Hello and welcome dear students. Today we are going to discuss an important topic, that is surface ocean currents. In this module we will learn about the continuous massive flows of water known as surface ocean currents, which act like massive rivers and conveyor belts across the globe. These currents are the wind driven movements in the upper ocean that play a critical role in regulating our planet's climate and weather. We will explore the primary forces that initiate this movement, the friction of global wind belts, and the powerful invisible forces that steer them, specifically the Coriolis effect, which happens due to the Earth's rotation, and blocking effect of the continents. Now coming to the main topic, ocean currents are continuous movement of seawater acting like massive rivers flowing within the oceans. They can be broadly divided into two main types. The first one, surface currents. These are wind driven movements of water in the upper 400 meters of the ocean. They constitute about 10% of all the ocean water are the focus and is focus of this module. Second are the deep currents. These are formed due to differences in water density resulting from temperature and salinity variations. They make up the remaining 90% of the ocean through a process called as thermohaline circulation. Now we will discuss the origin and controlling factors of surface ocean currents. The surface ocean currents are crucial regulators of Earth's climate. While equatorial regions absorb a disproportionate amount of solar energy, they are prevented from continually overheating because these powerful ocean currents and global wind belts effectively transport excess heat from the lower latitudes, which are also known as tropics, towards the higher cooler latitudes known as poles. Surface currents are born from the friction between moving air and the sea. As wind sweeps across the ocean, it literally grabs the top layer of water and drags it along. If Earth were a perfect water world without continents, currents would move in a simple bands following the planet's wind belts. However, in reality, the flow of ocean currents is more complex. It is not driven by wind alone, but by the interaction of three factors. The first one is the wind drag. Now we all know the moving air is called wind. As air molecules are driven across the sea surface in the wind, they bump into water molecules at the ocean surface. The energy transfer by frictional drag, if prolonged, raises waves and generates currents. The next are the pressure gradients. A pressure gradient is a simply change in pressure measured across a horizontal distance. The larger the difference in pressure over that distance, the steeper the gradient becomes. When water forms a mound, it creates a high pressure zone because that taller column of water weighs more and exerts more downward force. This can be explained by a simple formula: rho is equal to gh, where h is water height and g is the gravitational effect of the Earth. The third important and interesting factor is the Coriolis deflection. Due to Earth's constant rotation, ocean currents experience a tug known as Coriolis effect. This force causes moving water to veer towards the right in the northern hemisphere and towards the left in the southern hemisphere. As a result of this, water does not simply slide straight down a pressure gradient, that means from high to low. Instead, what happens? It travels at an angle. Another important factor is that is known as Ekman spiral. Ekman transport and geostrophic flow. We now understand the three forces that control the surface currents. Wind initiates the movement, pressure gradient dictate the slope, and the Coriolis effect provide the necessary deflection. But how deep does the wind's influence penetrate, and precisely at what angles does the water flow relative to the wind? To answer this, we must turn to the scientific explanation developed by V. Wilfred Ekman, which describes the complex vertical and directional movement of wind driven by water. Now, this Ekman spiral and Ekman transport, this is the vertical movement. In the northern hemisphere, surface water does not just follow the wind in a straight line. Because Earth is spinning, the Coriolis effect tugs on the water, forcing the very top layer to flow at an angle of roughly around 45 degree to the right of the wind's path. Through this frictional drag, this top layer sets the underlying layer in the motion, which moves slower and is deflected even further to the right. This process continues downward with each deeper layer moving slower and turning further right, creating a spiral shape. After this, we will come to the geostrophic flow, the horizontal balance. This includes the water mound formation. In subtropical gyres, trade winds and westerlies drive Ekman transport inward towards the center of the ocean basins. This causes water to literally pile up in the center, subtropical convergence, creating a hill of water that can be up to 2 meters of height. Now, vertical motions. There are of two types, either it can be upwelling or it can be downwelling. While horizontal currents transport heat globally, vertical motions are vital for mixing the ocean and distributing nutrients and dissolved gases. These vertical motions are critical because they connect the surface biology to the deep ocean reservoir. Now, upwelling. The upward movement of cold, deep, nutrient-rich water to the surface, while as downwelling is the downward movement of surface water to the deeper parts of the oceans. Coming to now the equatorial upwelling, or also known as divergence. Current divergence takes place when the surface water move apart and flow away from a specific region on the ocean surface. As the trade winds blow across the equator, Ekman transport pushes water north of the equator to the right northwards and water the south of the equator to the left southwards. The net result is a divergence of surface currents directly along the geographical equator. This divergence creates a void that is filled by the upwelling of cold, nutrient-rich water from below, supporting a high biological productivity. After this, we will try to understand the current convergence and downwelling. Now, this current convergence happens when surface water flow towards each other and they collide. Because water has nowhere else to go, it stacks up and is forced to sink. This vertical movement is called downwelling. A classical example occurs in the North Atlantic Ocean, where the warm waters of the Gulf Stream meet much colder flows like the Labrador Current and the East Greenland Current. After this, we will try to understand what is the coastal upwelling and downwelling. The proximity of a coastal significantly modifies this Ekman transport, leading to localized vertical motions. Coastal upwelling. Along the west coast of the continent in the northern hemisphere, such as along California, winds blowing from the north, generally parallel to the coast, cause Ekman transport to move water away from the shoreline towards its right. Colder water then rises from the below to replace the displaced surface water. In case of the coastal dwelling, what happens? If the winds are from the south, Ekman transport still moves this coastal water to the right, but in this case, water is pushed towards the shoreline. This stacking of water forces the surface water to sink in a process called as coastal downwelling. There are certain other drivers for upwelling. While Ekman dynamics are the primary cause, upwelling can also be triggerized by some localized effects, which includes offshore winds. Winds blowing directly away from a shoreline push surface water out to sea. Seafloor obstructions. When the current hits a submerged seamount or ridge, the physical barrier forces water upwards. Apart from this, it is also depend upon the coastal geometry. A sharp bend in a coastline can cause localized divergence of currents, drawing water up from below. Now, here we will start to discuss about the subtropical gyres, their structure and components. The large circular moving loops of water that are driven by the major wind belts of the world are called as gyres. The gyres means a circle. There are 5 subtropical gyres. The first one being the North Pacific Gyre, the South Pacific Gyre, the North Atlantic Gyre, the South Atlantic Gyre, and the Indian Ocean Gyre. Generally, each subtropical gyre is composed of 4 main currents that flow progressively into one another. We will discuss them one by one. Equatorially currents driven by the trade winds blow from northeast in the north and southeast in the south. These travel westward along the equator. Their role is from the equatorial boundary of the subtropical gyres. Western boundary currents, these are driven by the continents and the Coriolis effect, which deflects flow away from the equator. The moment is that they travel along the western edge of the ocean basins, for example, the Gulf Stream and the Brazil current. Note, these currents cannot cross land, so they are forced to turn towards the poles. Northern or southern boundary currents are driven by prevailing westerlies, and their moment is that these winds push surface water eastward across the ocean basins. For example, the North Atlantic current and the Antarctic circumpolar current. Eastern boundary currents. These are driven by the Coriolis effect and the continental barriers. Their movement is governed by due to the turn towards the equator along the eastern edge of the ocean basins. For example, the Canara current and the Bengaluru current. This completes the circular loop of this subtropical gyre. Warm and cold ocean currents based on temperature, ocean currents can be classified as warm currents. Now, these warm currents originate near the equator and travel towards the poles. Naturally, they are warmer than the water in their travel area. Compared to this, the cold currents, as the name suggests, the temperature of cold current is less than the water where the currents travel. They originate near the poles and subpolar regions and move towards the equator. Surface current systems by oceans. Currents of the Atlantic Ocean. To the north and the south of the equator, there are 2 westward moving currents, which are known as north and south equatorial currents. Between 2, there is a counter equatorial current which moves from west towards east. In northern hemisphere, north equatorial current, the north equatorial current is significant Atlantic Ocean current that travels from east to west between the latitudes of 10° north and 20° north. Now, the current system direction and their location plays a characteristic and its role in the north equatorial currents. They flow from east to west and from westwards between 10° and 20° north. It is separated from the true equatorial circulation by eastward flowing equatorial countercurrents. Antilles current is a part of the combined equatorial flow that moves poleward along the eastern side of the West Indies. It forms the initial warm poleward path of the Gyre. Florida current, part of the combined flow that enters the Caribbean Sea and Gulf of Mexico, existing via the Florida Strait. This strong warm current moves along the southeastern coast of the USA up to the Cape Hatteras. Gulf Stream, one of the most popular streams. Gulf Stream starts beyond Cape Hatteras and continues to flow strongly northwest towards the Newfoundland. This is a classic example of warm, fast, narrow western boundary current. Another important current is the Labrador current, a cold current flowing equator along the eastern coast of Canada from the Arctic Ocean. It meets the warm Gulf Stream near the northeastern coast of the USA. North Atlantic drift, the Gulf Stream is deflected eastwards by the westerlies and the Coriolis effect crossing the Atlantic. This powerful warm current transports significant heat far into the North Atlantic, maintaining a milder climate. Norwegian current, the northern branch of the North Atlantic drift that flows along the coast of Norway. It continues to transport from water, keeping Norwegian ports ice-free during winter as it enters the Arctic Ocean. Canaries current, the southern branch of the North Atlantic drift that flows equator between Spain and Azores Islands. This is a cold, slow, wide eastern boundary current. Equatorial countercurrent flows from west to east between the north and south equatorial currents around a latitude of 3 degree north to 10 degree north. This current replaces the water removed from the eastern side of the ocean by the two equatorial currents flowing westwards. Now, Atlantic Southern Hemisphere South Equatorial Current. The South Equatorial Current is a major Atlantic current that travels from east to west, driven largely by the trade winds. While its main path is located between the equator and roughly around 20 degrees south latitude, it behaves uniquely in the Atlantic compared to the other oceans. Brazil current. Brazil, in the southern Atlantic, the south equatorial current travels westward until it hits the coast of Brazil, while it turns south and flows along the continent's eastern edge as the Brazil current. Bengaluru current, as a part of a western wind drift or the Antarctic circumpolar current, merged with the southern current. The currents, while crossing the Atlantic near the Cape of Good Hope, the South Atlantic current is diverted northwards as the cold Bengaluru current. Current systems, direction and their location and characteristic role. South Equatorial current. This flows from east to west between the equator 20 degrees south. This strong current initiates the gyre. Brazil current, as already discussed, the main branch turns southward, flowing along the eastern coast of South America. Brazil. This is the warm southward moving westward boundary current of the South Atlantic gyre. Another interesting current is the Falkland current. It's a cold current flowing northward along the southeastern coast of South America from the south. The current meets the warm Brazilian current around 35 degrees south latitude, creating a zone of thermal mixing. Now, there is another current that is known as South Atlantic current. The Brazil current is deflected eastwards around 35 degrees south due to the influence of the westerlies and the Coriolis effect. It crosses the Atlantic effectively, merging with the west wind drift. Bengaluru current, the South Atlantic current, is diverted northwards near the Cape of Good Hope. This is a cold, slow, wide eastern boundary current of the gyre. Now, as we have gone through the currents of the Atlantic Ocean, we will discuss the currents of the Pacific Ocean. Pacific Ocean, Northern Hemisphere, the North Pacific current system follows a massive circular route, a gyre that connects Asia and the North America. Equatorial current is that travels westward until it hits the land masses of the Philippines and Taiwan. Another one of the most famous currents from the Pacific Ocean is Kuroshio Current. The water turns northward past Japan. This is a warm current similar to the Atlantic Gulf Stream. The northern collision, called the Ostock Current, flows down and merges the Oishio Current. Northern collision, the cold Ostock Current flows down and merges into the Oishio Current. The cold Oishio then meets the warm Kuroshio of the coast of Japan. North Pacific Current, driven by westerly winds, the water turns eastward and flows across the open ocean towards the North America. The split at the North America, upon reaching the coast, the current divides into two. One is the Alaska Current, its northern branch, a warm flow that moves counterclockwise along the Alaskan coast, and another is the California Current, the southern branch, a cold flow that travels south along the US west coast. The circuit completes. The cold California current eventually turns west and reunites with the North Equatorial Current, closing the loop. Now, Pacific Ocean southern hemisphere, the South Pacific Current system forms a massive counterclockwise loop known as a subtropical gyre. You can trace the circuit through these stages. South Equatorial Current, driven by the winds, this water travels westward across the Pacific. East Australian Current. Upon hitting the Australian coast, the water turns southward. This is a warm current. Another is South Pacific Current. After passing Tasmania, the flow is pushed eastward across the open ocean. This is a cold flow that moves in coordination with the west wind drift. Peru-Humboldt Current. As the water reaches South America, it turns northward along the coast, and thus what happens? The circuit completes. The cold Peru Current eventually flows back into the South Equatorial Current, closing the giant loop. Now, we will see the currents of the Pacific Ocean current system, their direction and location and their role. North Equatorial Currents flows westward, initiating the gyre, forms the southern leg of the gyre driven by the trade winds. Kuroshio Current flows northward along the coast of the Philippines, Taiwan and Japan. This is the warm, fast, narrow western boundary current of North Pacific, also known as Kuroshio. Oishio Current flows southward along the eastern coast of the Kamchatka Peninsula. This is a cold current that meets the warm Kuroshio Current, creating a highly productive fishing ground and a foggy zone. North Pacific Current. The combined Kuroshio flow is deflected eastward by the westerlies, flowing right across the ocean. It is a massive transport current that carries water across the basin. Alaska Current. The northern branch of the North Pacific Current, flowing anti-clockwise along the coast of Alaska. This branch is warm and helps moderate the climate of the Alaskan coast. California Current is another current, the southern branch flowing southward along the coast of California. This is a cold, slow, wide eastern boundary current. Equatorial countercurrent flows eastward between the north and south equatorial currents around 3° north to 10° north. This current replaces the water removed from the eastern side of the Pacific by the equatorial currents. Now, we will discuss about the currents of the Indian Ocean. The circulation of the currents in the Indian Ocean follows a unique pattern compared to Atlantic and the Pacifics. Northern hemisphere during winter. In the winter months, the island of Sri Lanka serves as a natural barrier separating the currents of the Arabian Sea from those of the Bay of Bengal. During this time, both regions are dominated by the northeast monsoon winds, which pushes the surface water westwards. Indian Ocean in the northern hemisphere during the summer, the northern section of the oceans fall under the influence of the southwest monsoon. This shift causes the surface waters in the Arabian Sea and the Bay of Bengal to move eastwards in a clockwise direction. Indian Ocean southern hemisphere. The movement of the water here follows a large counterclockwise loop. South equatorial currents, they are driven by the winds from east to the west. This current is recharged by the water entering from the Pacific Ocean. Mozambique current. When the water hits Africa, parts of it funnels southward through the narrow channel between the mainland and Madagascar. Agulhas current. The different branches reunite south of the Madagascar to form this exceptionally powerful warm current flowing along the South African coast. West wind drift. The Agulhas eventually hits the cold massive Antarctica circumpolar current which carries the water eastward across the bottom of the Indian Ocean. West Australian current. A portion of that eastward flow breaks up and heads north along the coast of Western Australia. Now this loop closes. This cold water eventually turns west again to rejoin the south equatorial currents, completing this giant circular circuit. Now we will discuss the currents of Indian Ocean, their current system and direction and their characteristic role. South equatorial currents flows east-west across the ocean. It is often strengthened by a water flowing from the Pacific Ocean initiating the gyre. Mozambique current which flows southward along the coast of the Mozambique, Africa. This is the warm poleward flow that begins the western boundary current system. Agulhas current formed by the confluence of the Mozambique current and the water flowing between the mainland and the Madagascar. This is the warm, strong western boundary current of the Indian Ocean. West wind drift. The Agulhas current merges with the west wind drift near the Antarctic circumpolar current and it turns eastward across the Indian Ocean. This connects the Indian Ocean to the cold continuous global flow. Western Australian current. A branch of the merger current flows northward along the western coast of the Australia. This is the cold equatorial moving eastern boundary current. Now, significance of surface ocean currents. Ocean currents and climate. Ocean surface currents directly influence the climate of adjoining land masses. For instance, warm ocean currents, they warm the nearby air. This warm air can hold a large amount of water vapor which puts more moisture, high humidity in the atmosphere. When this warm moist air travels over a continent, it releases its water vapor in the form of precipitation. Ocean currents also influence the marine and ecosystem. Nutrient distribution. Ocean currents can transport nutrients across vast distances, influencing the distribution and abundance of phytoplankton, basis of the marine food chain, like the Gulf Stream, which is a powerful ocean current that transports warm water from the Gulf of Mexico to the North Atlantic. Significant impacts of coastal environment. Strong ocean currents can cause erosion along the coast, wearing away beaches and cliffs over time. Impact of water mass on the climate and marine life. The movement of water masses has profound effects on the marine environment. It can lead to oxygen depletion in deep waters, creating dead zones where marine life struggles to survive. Dear students, this was all about today's program. Hope you have enjoyed it well. Thank you for watching.